Hello and welcome to our lesson on completing the square. Today we'll uncover a new approach that will make your handling of quadratic equations both versatile and insightful. In this lesson, we'll expand on our previous knowledge by introducing a new method to solve quadratic equations, distinct from factorizing. We'll start by understanding completing the square, seeing how it offers another way to solve quadratic equations. We'll then compare this technique with the method of factorizing to find roots. After that, we'll go through some practical examples to see this new technique in action and understand its applications. So far, we've been working on solving quadratic equations by factorizing them to find their roots. You've become skilled at breaking down these equations into their factors and identifying the points where they intersect the x-axis. With this foundational knowledge, we are now ready to dive into another powerful method for solving quadratic equations, completing the square. This new technique not only adds to your mathematical toolkit, but also provides alternative ways of understanding and solving problems where factorizing might be less straightforward or inefficient. Imagine encountering a quadratic equation where factorization seems cumbersome or unclear. This new method will give you a reliable and often more efficient way to solve the equation, broadening your problem-solving capabilities. Let's get started. We'll start by introducing perfect squares. A perfect square quadratic is an expression that can be written in the form ax plus b squared. This is different from expressions like x plus 1, x plus 2, where the two factors are different. For example, x squared is already a perfect square since it can be written simply. Another example of a perfect square is x squared plus 4x plus 4 since it can be written as x plus 2 squared. The factorization of a perfect square quadratic results in just one term squared, which gives us just one root. Graphically, this happens when the quadratic represents a parabola which touches the x-axis at exactly one place as shown. This is the graph of x squared, which has exactly one root at the origin. This idea of perfect squares helps us when we try to solve quadratic equations where factorization is not straightforward. The main aim when completing the square is to transform a given quadratic equation into a perfect square form as closely as possible. Let's break down the method for completing the square with a step-by-step example. Consider the quadratic equation x squared plus 4x minus 7. It's not easy to solve this by factorizing, so we look to complete the square. Start by focusing on the x squared and 4x terms. We want to form something like ax plus b squared. When we expand this, we get the following. This tells us that the 4x term comes from 2ab. Here, ai is 1 since there is no coefficient in front of the x squared term. Hence, we need to find b such that 2b equals 4. Solving for b, we get b equals 2. So we have found that a equals 1 and b equals 2. Let's input this into the form ax plus b squared to get x plus 2 squared. Expanding x plus 2 squared gives us x squared plus 4x plus 4. Notice we are close to our original expression of x squared plus 4x minus 7, but we have a plus 4 at the end and we need a minus 7. We can adjust the expression by subtracting 4 and then also subtracting 7. Simplifying, we get x plus 2 squared, minus 4 minus 7, which equals x plus 2 squared, minus 11. Our equation x squared plus 4, x plus 7 equals 0, now becomes x plus 2 squared minus 11 equals 0. Solving for x, we add 11 to both sides. X plus 2 squared equals 11. Taking the square root of both sides, we get x plus 2 equals plus or minus square root of 11. Make sure to not forget the plus or minus, since we do not want to miss out any solutions. Finally, rearranging for x, we get x equals minus 2 plus or minus root 11. So the solutions are x equals minus 2 plus root 11 and x equals minus 2 minus root 11. Completing the square shows us another way of finding the roots of the quadratic equation, which are the solutions we've found where the equation equals 0. This completed square form is also very useful for finding the turning point or vertex of the quadratic. Let's see how we can do this for our example of x squared plus 4x minus 7. If we ignore solving for y equals 0 and rewrite our expression, we get y equals x plus 2 squared minus 11. To find the turning point, we need to determine where y is at its lowest, or highest if the coefficient of x squared is negative. A squared term is always non-negative, and so the right-hand side of this equation is minimized when the expression inside the bracket equals 0. We want to find the point when this occurs, so we set x plus 2 squared to 0, giving us x equals minus 2. Substituting x equals minus 2 back into x plus 2 squared minus 11, we get y equals minus 11. Thus, the turning point of the quadratic is minus 2 minus 11. By completing the square, not only do we find the roots of the equation, but we also gain insights into the properties of the quadratic function, such as its turning point. This technique offers a powerful alternative when factorizing methods are not straightforward. Generally speaking, the turning point of the quadratic ax minus b squared plus c is bc. Let's dive into applying this new technique for solving quadratic equations. Now let's try this. 2x squared plus 8x plus 6 equals 0. Step 1. Divide the entire equation by the leading coefficient, which is 2. This gives x squared plus 4. X plus 3 equals 0. Step 2. Then move the constant term to the other side. This gives x squared plus 4x equals minus 3. Step 3. Take half of the coefficient of x, which is 4, square it and add it to both sides. Half of 4 is 2 and 2 squared is 4. Therefore x squared plus 4x plus equals minus 3 plus 4, which simplifies to 1. Step 4. The left side is now a perfect square. X plus 2 squared equals 1. Step 5. Now take the square root of both sides. So x plus 2 equals plus or minus 1. Step 6. And finally solve for x. X plus 2 equals 1 or x plus 2 equals minus 1. And therefore x equals minus 1 or x equals minus 3. Here, we have found the roots using the completing the square method. By completing the square, we have again found the roots of the quadratic equation. This method of completing the square can sometimes simplify the process of solving quadratic equations, especially when factorization is not straightforward. It also provides insight into the structure of quadratic expressions and helps in understanding their graphical representations. In today's lesson, we explored the technique of completing the square as an alternative method for solving quadratic equations. We began by revisiting the concept of perfect square quadratics, where expressions can be rewritten in the form ax plus b squared. This understanding set the stage for us to compare this technique with factorizing to transform more complex quadratic equations into a perfect square form, thereby simplifying the solving process. We then walked through the steps of completing the square, illustrating how to convert a quadratic equation into a perfect square plus or minus a constant. By doing this, we were able to solve for x by isolating the squared term and taking the square root of both sides of the equation. Additionally, we highlighted how this method not only helps in finding the roots of the quadratic equation, but also provides insights into the function's properties, such as its turning point. Completing the square allows us to easily identify the vertex of the quadratic, which is especially useful in graphing and understanding the behavior of the quadratic function. Overall, this technique offers a valuable alternative to traditional factorization methods, broadening our problem-solving toolkit and enhancing our ability to tackle a variety of quadratic equations efficiently. Watch the rest of the GCSE Maths course at Sophos Education.